Okay, ladies and gentlemen, our next session is about streaming video on the Apple II. Take it away.
How about now? There we go. Cool. Right, so actually, if we could just switch back to the laptop just for a second. So yeah, I'm going to be talking about a project that I've been working on for about 6 months, which is streaming video on an Apple II. I'll start with a demo, and let me give some context about what you'll see. So I'm streaming from this 2GS, which is pretending to be a 2E. So I'm only using 8-bit features, so 1 megahertz, 64 kilobytes of RAM. I'm using double high res, so it needs that. And the sound you'll hear is from the normal good old Apple II speaker. It's the thing that knows how to tick. So basically I'm using the 2GS as for its audio output. That's the audio out socket, that's all I'm using. And I'm streaming this from my laptop here using an Uthernet II. So that's the main piece of hardware. That's the key that I need for this to work. I do have a CFA in there, but that's just for convenience. So this should work on everything going back to the original 64K Apple II from 40 years ago. I haven't tested it on anything apart from the 2GS. I hope that I'll be able to have the opportunity to do that maybe later today or sometime this week, because I saw lots of machines here that we could try with. Okay, so let's switch over to the and let's see what happens.
Remember how we started not so long ago. We dreamed of giving everyone a personal way to grow. Our dream became reality, and now we're making and let it lead the way to a new world of discovery, touching lives every day, bringing smiles to children's faces, opening doors to brand new places. Apple II forever.
I apologise to everyone who's going to have that song stuck in their head for the rest of the day. Actually, I think that was from the 2C launch announcement, so maybe Mark was lucky enough to see that live. I don't know. Lucky. Anyway, so let's dig into what's going on here. So I'll start with the bit which isn't new, which is the audio. So as I mentioned, the Apple II speaker just basically knows how to tick. It can move in or out and make a tick sound when you access a memory location. And so there's an old technique going back to at least 1990 or so as far as I know, which is called pulse width modulation, which is where you control the duty cycle of that speaker cone. So you don't allow it to move all the way in or out, but you turn it on and off very precisely, and you allow it to move during some fraction of each time interval. And by doing that, you can actually modulate a high frequency carrier wave with some lower frequency audio, and then simulate higher audio bit depth. So here, this is using a 14.3 kilohertz carrier, which it's not ideal. The state of the art for this sort of thing is to use a 22 kilohertz signal, which is beyond the audible range. At least with the built-in audio, the built-in speaker on the 2GS, the high frequency response isn't very good, and so you don't really hear that 14 kilohertz tone. At least my aging ears don't hear it. With the amplified audio, we had to tune down the treble, the 10 kilohertz band to get that under control. So let's look at that, what it looks like in code. So this is how you'd write such a player. So the key is to count the cycles and control when you access the speaker, and then when you access it again. So here in this example, we're ticking the speaker, we're waiting 12 cycles, we're ticking it again to turn it to bring it back in, and then we wait, we pad out so that every time we run through this routine, we take the same length of time, 73 cycles, until we're back to the next tick instruction. So there's a lot of waiting in this, in that code. It's basically just ticking the speaker, waiting, ticking a bit. And so if you're doing this with a RAM-based player, that's where you'd have to do all the work. You'd have to deal with stepping through memory, decoding the next sample, figuring out where to jump to, and so on. And you'd probably be willing to trade some CPU cycles for better memory density, because even, this 22 kilohertz player gets about 4 seconds of playback from 48 kilobytes of memory. So it's really quite memory intensive. So anyway, fast forward to the start of the year, I bought an Uthernet II card, and I'm trying to work out what to do with it. There's some cool software, we saw some of it just before, but I wanted to learn about this thing and start to play with it. And so I was reading the manual. It's got this thing called a W5100 controller on it, and that has a feature where you can auto-increment through the memory space. It's got an onboard 16 kilobytes of RAM, and it's exposed to the Apple as an I/O location where every time you access it, you read or write a pointer in the onboard memory that steps through on its own. You don't have to worry about incrementing the pointer yourself. It just happens every time you read it. And it occurred to me this is the fastest possible way you can get data into the machine, short of some sort of direct memory access, because you're really doing no work apart from just give me some data, give me some data, give me some data. And so I was thinking, well, what can I do with this? And I started wondering about video playback. I didn't know if it was possible. And actually, that was the first thing I did was write a little video player. It turns out that is really efficient. You can actually fit that in the 0 page if you want, just doing video. So then audio is much trickier because it's really timing intensive. Your ear is very sensitive to any differences in frequency there, and so that's really where the cycle counting happens. So let's start with that audio snippet that I showed you and start hanging things off of that chassis and work towards doing the video playback. In other words, we're going to fill in those wasted cycles there with reading things from the TCP stream and then doing things with them. And for now, I'm going to ignore the the stream management. So we've only got 8 kilobytes of socket buffer to work with, and we'll have to figure out what to do when we fall off the end, but I'll come back to that. So here's the basic code structure we saw before, but now we're going to, at the end here, when we want to figure out what to do next, well, we could do some computation, but that's going to be pretty expensive, so let's just ask the TCP byte stream. We'll read a byte from the stream, and then self-modify our address here to figure out where to jump to next. So the Apple doesn't know, the Apple doesn't care. We're trusting that the data we get from the remote end will tell us what to do. So next, well, if we're going to do video, we'd better start storing some bytes to memory. We need to figure out what to store. So again, we can ask the data stream, what byte should I store? And now we'd better start putting that in memory. So because we're dealing with video streams, images, there's a lot of redundancy there. And it's going to be okay if we actually introduce some errors. We don't have a perfect fidelity image, as long as it's not too bad. So what we can do then is we can store the same content byte at different places on the screen. The way that the high-res screen is structured, it's page-based. We need to store data into different offsets into a page. So we can read an offset from the stream, here we're indexing into hex 20 page, and storing our content byte there, and they're doing the same thing 3 times. And so it turns out you have some cycles left over, but this is useful to be able to juggle things around in some of the cases later on. So what we've got now is the ability to read an arbitrary, or to store an arbitrary byte value at 4 arbitrary offsets onto a given high-res page. And while we're managing the speaker, we're ticking the speaker at some constant rate. So far I've showed you doing it for hex page 20. There's 31 other screen pages, but we can just copy the same basic structure 31 times. We need to also worry about other duty cycles for the speaker, and that gets a bit trickier because we have to rearrange those 2 tick opcodes to have them a different time interval apart. And there's some fiddliness needed there because you have to rearrange things, and actually 2 of them I couldn't get quite right. They're off by 1. But altogether, if we multiply this out, we've got 1,024 of these variants, and it turns out these just fit in main memory together with ProDOS. So that was kind of remarkable. I mean, this didn't have to be the case. Maybe, it was too much to fit, but it does. Okay, but we still don't know, is this actually useful for playing back video? So we can do a quick calculation here. We're storing 4 bytes to the screen every 73 cycles, about 57,000 per second. And that's enough to do about 7.5 complete refreshes of the screen per second. So given that a typical video is not going to be changing every byte, every frame, this seems like it's right in the right ballpark, assuming we can manage the errors that we'll be introducing. Anyway, so let's watch on the video. If I could switch back to the... leave it there and leave you wanting more, just for lack of time. So let's recap. So what we've built is a player that knows how to read data from the TCP byte stream and then use that to steer the CPU to spray bytes at 4 different offsets on a memory page that's within the high-res screen page 1. And it does this while also steering the speaker cone to modulate this 5-bit audio. So an interesting thing is that so far we haven't actually used any conditional 6502 opcodes. The player is just completely deterministic. It's doing exactly what the bit stream tells it to do. But the caveat here is that we can only read 8 kilobytes of data before we fall off the end of the socket buffer and have to do something about that. So how do we deal with that? So we actually don't want to use the full 8 kilobytes because then we would actually probably stutter if we had to wait while that refills. So it turns out 2 kilobytes is a good compromise. We read 2K at a time. And we could do some byte counting and try and work out when we're hitting that limit and need to do some work. But because this playback is deterministic, we can actually just rely on the server to tell us when it's time to go and manage the socket buffers. So every 2K in the stream, there's an opcode inserted which jumps to the slow path that needs to go and manage the TCP buffers. So it has to move the read pointer in the socket buffer, tell the card to act the TCP stream, and then wait till the buffer has at least 2K more. And the tricky part here is that we also need to keep managing the speaker during this period. So every 34 cycles, we need to keep ticking the speaker so we don't introduce too much background noise in the audio. And it turns out you can do this in 2 of these 73 cycle periods that we have. So that means that every 292 audio frames, we have these 2 dead frames where we're managing TCP, but that's less than 1% of noise, so that's actually not too bad. Okay, so that video we saw at the beginning was double high res. So what's going on there? So at runtime, double high res requires us to flip a soft switch to switch between writing to the main memory and auxiliary memory. So we're going to have to flip back and forth to steer writes between these places. And that's got some overhead. So we probably want to do that only every now and then, not every byte. So we already have a place where we're doing some periodic processing. So let's just do that in this slow path where we're also managing the TCP buffers. So we use the same strategy. We'll read a byte from the stream. We'll self-modify to interpret that as the address of a soft switch to toggle, and then we toggle that soft switch. So it comes down to basically making this change to the player. So the thing I just said, we read a byte, we store it into a soft switch address, and then we flip it. So there's a bit more timing fix-ups and some initialization, but it came down to basically this very small change to support doing that in the playback. So the cost of this is that because we're only doing this every now and then, there is some interlacing that happens where you're first writing to main, then aux, and switching back and forth. But it's usually pretty reasonable. It doesn't show up very often. Okay, so we've got a player that is capable of playing back a high-res or a double high-res video stream with audio. But we need to give it something we need to give it one. And so this turns out to get this to have good quality, we need to understand a fair bit about how the color graphics are actually represented on the display in order to know what to give it. So rather than me telling you about this, let's ask this guy. And we'll do another demo.
TV, the world is thinking.
The idea came. Luckily, it either comes to you or it doesn't sometimes to solve these things, like putting color into computers. That was probably one of the biggest things Apple ever did. Nobody expected color to come into a computer because color machines cost $1,000. to generate color. They had tons of chips, and I figured out a way to do it with one little $1 chip. And it was really strange how it happened. But this would apply to young children. I was without sleep for 4 days and nights because Steve Jobs and I got a project to design a game for Atari called Breakout. He said Steve needed the money quick, so we had to do it in 4 days and nights. I didn't think it was possible. Back then, games weren't software. They were hardware. Little chips and voltages to wires from here to there make it work. And I didn't think it was possible, but I said, I'll try it. And I designed the whole thing, and we got it done in 4 days and nights. But when you're without sleep, when you're going to sleep, your head goes briefly into this period of really creativity, kind of thinking. It's not restricted to the normal thoughts of life and the day. When you're waking up, your head's a little like that. Well, my head was kind of in this floating, half-asleep state, and out on the Atari floor, they only had black and white TVs in those days for the first arcade games. They had this dot going across the screen. It's changing colors like a rainbow, and it was hypnotizing like you're at a concert or something. And they just put little strips of Mylar, red, green, blue, yellow, on the TV screen to do it. And I started thinking that was so beautiful, and I remember exactly what bench I was at. Steve was wiring up the board over there, and I'm right at this one bench. I just sort of drifted, and I thought, signals for color TVs. I remember from high school electronics, they go up and down at a certain speed. And then I thought, what if you made a signal that went up and down at a different rate? Would it look like color? Just a digital, the normal simple thing I can do with almost no parts at all. Would it look like color? And then, oh my gosh, I figured out a way that I could have four little 0-1 bits circling around, and it could go up and down at different time, and red would become blue. I could put in a different pattern of ones and zeros. I had 16 patterns, and it could become a different shade. It might be a little lighter, and it might be a little darker. Would it work? And didn't know. But when I finally wired it up about a year later, and brought Steve over, we saw it, and that was eureka. We knew this was a big change in the world.
Mm-hmm. So, if anyone's ever been confused by high-res colors, try going 4 days without sleep. Maybe it will make sense. So anyway, to summarize what he said, but actually I'm going to give a lightning talk about that tomorrow. So I'll go into more about exactly how color works, or at least a model for understanding how color works, because it's more complicated than I understand. Let's talk about how to produce these videos. So, first we have an input video file, like an MP4 or something. We need to break it apart into the audio stream and then the sequence of video images. The audio stream is not that complicated to deal with. We have to downsample it. We have to normalize it. A trick here is that I'm actually downsampling to 14.7 kilohertz, not 14.3. This gives better quality because it's an integral divisor of 44.1, which is the usual audio bit rate of these streams. So that's only about 3% error, so that's not too bad. On the video side, I'm using a program called BMP to DHR by Bill Buckles to turn the video images into an Apple II memory representation, an image file. And then from that, I'm computing the color representation of what that memory frame would look like on the Apple. And this is what I'll go into tomorrow. So the core of this is, what do I do with that? I have this sequence of two memory images, Apple II screen memory images. And I probably can't transmit the entire contents because I don't have enough time before the next one's going to arrive. So I have to choose I have to prioritize what content to send in what order. So if you remember back to the beginning, the things I need to provide to the player are the content byte to store on memory, which page to store it on, and then 4 offsets to store it at. And so I have to choose, produce a sequence of these which will maximize the perceived quality of the image. I'll come back to that in the next slide. But suppose I've done that. Now I have a sequence of these tuples, and I need to. I then just multiplex them back together with the audio stream, and this tells me the sequence of player opcodes of the form that we saw at the beginning. Then I just need to compile them into a byte stream. That's just basically saying that because the Apple needs to receive the exact memory addresses of these opcodes. So it's tailored for a particular version of the player. And so if I change the offsets in the player code, I have to recompile all the videos. And then finally, I have to insert these slow path opcodes every 2 kilobytes to tell the Apple to go and manage the buffers. Okay, so let's talk about how I choose the sequence of contents to actually produce the highest quality image that we can do. So the key is to look at to choose them such that they minimize the visual difference between the current contents of the screen and then the target we're aiming for with the next frame. So we want to work in priority order, so we send the data that's going to resolve the most amount of visual difference first. So this is going to prioritize the large differences between one frame and the next. And we may or may not get enough time to get around to sending everything, so the fine detail may not get resolved, but anything that's left, any residual errors, accumulate to the next frame. So we're more likely to fix them next time if they're still there. So it all comes down to this perceptual distance metric. So firstly, the human eye is pretty complicated. Some colors are perceived as being very different than others. For example, yellow is pretty close to white, but like dark green is not close to white. And when we're having to make a choice about, I can't send exactly the right byte, but I can send one that's close. How close is close? And so this is important to understand, when I should make a substitution. So I'm using this thing called a CIE 2000 perceptual color difference metric. I read about it on Wikipedia. There's lots of these attempts to model the perceptual, the visual system, how the eye perceives color. And so now I know how to tell 2 colors apart and give a number that measures how far apart they are. I need to know what is the set of colors that will be displayed on the screen if I were to store a given byte at a given offset. And so I can look at the content, the colored pixels that are generated by a given byte as it is on the screen now, and then as I want it to be in the future. And it's not just the pixels from the byte itself, because there's some influence from pixels on either side. So it's a bit wider than the 7 or 8 bytes that you actually store. So now I have these colored pixel strings which I'm comparing. And so I'm using an edit distance metric between these 2 strings. And it's something called a Demerel-Levenstein metric, which is basically just measuring. It takes into account these strings can be made more similar by transposing 2 pixels, so moving something left or right. And there's some cost to that, where it's, if a pixel shifts left, you're probably not going to notice, as well as the color differences that come from this other metric. And it turns out that you can pre-compute all these possible differences ahead of time. So you can pre-compute so in other words, all possible source bytes versus all possible target bytes. And so at runtime, there's just a big matrix that you give it the source and target, and then it tells you this number, which is how far apart they are. And so then that's the thing I want to maximize when I'm choosing these numbers. So this is all written in Python using NumPy, which is this fast array package. And it's about 5 to 10 times slower than real time, so it's not real time streaming, but it's, I'm sure if I rewrote the core of this thing in something like C, then it would be, it's within striking distance of real time. So what's left to do here? So I think there's a lot that could be done to improve the quality of the video stream. So I mentioned that I'm using BMP to DHR to give the sequence of image frames. And that was convenient when I started out, because I didn't have to worry about, like, how do you turn a 24-bit BMP or image into something which the Apple will understand, the bytes that go in memory. So I didn't have to solve that problem, but actually this is probably reducing my quality, because that process will introduce some errors. There's various assumptions that are made and optimizations that happen there. And then I'm also doing a second pass where I'm now deliberately introducing errors to produce the video stream. So I'm left with some sort of approximation of the true image. And I should be able to get better results if I directly target the original image frames. There's also, because I'm using this weird constraint where I have to store 4 bytes of the same type on the same page, I can probably get better control of the error diffusion if I like directly work with those constraints. The caveat is it's probably much more expensive to do, at least in Python, but that remains to be seen. On the audio side, there's not a lot of signal processing I'm doing, and you probably heard there are some audio artifacts there, some like pops and static and whatnot. I'm sure it's possible to improve that. Somebody who knows more about signal processing than me can probably tell me what to do. On the player side, you saw there's not really any UI there. It's just, it knows it will ask for a video and then play it. And there's a lot of hard coding that happens. The IP address that it talks to is hard coded. That should be pretty easy to fix because it's just a string in memory, so it's one place. The harder thing to fix is going to be that it assumes the Uthernet is in a particular slot, and because that affects the I/O addresses that it talks to, that's hard coded in like 1,000 places. So there's probably some way to fix that because I know what those addresses are, so you could write a patch routine that goes and fixes them up, but that's going to be more work to do. And then it would obviously be nice to have a file selector UI that lets you choose, which video to play in and whatnot. At the moment, I'm getting away with only one directional data transfer. It's all from the laptop to the Apple, so there's no bidirectional communication. And supporting any kind of stream seeking would either require real-time transcoding of the video, so you can actually switch from, wait, I thought it was over here, to now I'm over here, or you'd have a lot of video artifacts with, the stream is going to be interpreted as if it was somewhere else. Yeah, questions back.
Regarding the playback sleep, another way you can do it is emulate the state on the host machine to get to seek to like from the beginning to the point you want to seek to, send that whole frame, and then resume from that point to the execution.
Yeah, so
which is probably less computationally intensive than re-encoding.
yes, yeah, you're right. There might be some smart tricks there. Good idea. Yep. Yeah, and that's it. So the code is available there. So go and check it out if you're interested, or if you'd like to play with this more on different hardware or whatnot. Yeah, come and talk to me. Any other questions? Yes.
The slot number and like X register and then.
I could, but that would have a CPU cost to doing that. So in order to get it into the high byte of or wherever it is in the address, everywhere I'm doing the load of of the TCP stream, that's a different address to load from. So I would need to, yeah, maybe that would work actually. Yeah. Because actually I'm not using the X register. That's a trick. Yeah. Cool. That might be the easy way. Thanks. Any other questions? Yeah.
Just curious, sort of, where did you get the source video from? There's something at the front end there that you were able to chuck it into BMP to DHR.
Yep.
But I guess you've got to take that video frame and get it into a BMP. So I'm just wondering about.
Yeah. So I'm using a Python library that does that, I don't know how it does it internally. I don't particularly care for the purposes of this, but you give it a video file, and one of the things it will do it emits a. Yeah, it uses FFmpeg under the hood, so any of the supported video formats. Yeah, but yeah, the interface that I'm consuming there it just gives me a sequence of image frames. So yeah, that's a library for me. Yep. Okay, thanks very much.